Hello students, welcome to a series of mathematics program for grades 10 and 11. The topic for today is sequences. This is the first part of a series of 3 lessons on sequences. The objectives for today's lesson are: at the end of the lesson, you should be able to continue a given number sequence, to recognize patterns in sequences and relationships between different sequences, and finally, you should also be able to generalize sequences as simple algebraic statements. So let us start. Numbers are found and used everywhere in our daily life. In many situations, we see number patterns, or we may also find patterns involving figures. You can see here we have various examples of patterns in our everyday life. Pattern is a very important element in mathematics and a key part of algebraic thinking, because recognizing a pattern or relationship leads to the possibility of predicting or generalizing. A number sequence is a set of numbers that follow a certain rule. Each of the numbers in the sequence is called a term of the sequence. Number patterns can occur in different forms. The first one is what we call repeating patterns. In a repeating pattern, the numbers repeat themselves in a regular way. Let us consider these examples. First one, we see 4, 5, 4, 5, 4, 5. So we can see here that 4, 5, 4, 5 are being repeated. Second example, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So the numbers 1, 2, 3, 4 are being repeated in a regular way. These are repeating patterns. Next one we have is growing patterns. In a growing pattern, the numbers increase in an orderly and predictable manner. So here we have 4, 14, 24, 34. You can see that the numbers are increasing. Now, let us see what is happening in this pattern. How do we get the next term? Yes, you can see that we are adding 10 to get the next term. Part B, 2, 6, 10, 40. So here also the numbers are increasing. And what are we doing to get the next term? We are adding 4. The third one is the shrinking patterns. So here, in a shrinking pattern, the numbers will decrease in an orderly and predictable manner. Look at this example, 8, 5, 2, -1. you can see that the numbers are decreasing. In fact, we are subtracting 3 to get the next term. So we have to subtract 3 to get the next term. Part B, 15, 10, 5, 0. So here also we have a shrinking pattern because the numbers are decreasing, and we have to subtract 5 to get the next term. We also have some special sequences. The first one is what we call the sequence of square numbers. Do you still remember what is a square number? A number multiplied by itself will give a square number. For example, 6 times 6 equal to 36. And 36 is called a square number. So we have 1, 4, 9, 16. This is the sequence of square numbers because 1 to the square gives 1, 2 to the square 4, 3 to the square is 9, 4 to the square is 16. So we have a sequence of square numbers. Similarly, we have the sequence of cube numbers. So 1, 8, 27, 64 will be the sequence of cube numbers. Because 1 to the cube is 1, 2 to the cube is 8, 3 to the cube is 27, 4 to the cube is 64. Next, we have a sequence of prime numbers. So 2, 3, 5, 7, 11, and so on represent the sequence of prime numbers. We also have a sequence of triangular numbers. You still remember what is a triangular number? 1, 3, 6, 10 will form the sequence of triangular numbers. Look at these diagrams. You can see that the numbers 1, 3, 6, and 10, they are forming triangles. You can see here. Now, this can also be seen in real life. Look at the arrangement of the oranges. They are very similar to the figures that we have here. 1 orange, 1 dot. Here we have 3 oranges, just like here. 6 oranges, 10 oranges. So this is an example of sequences in real life. Now you have a few questions to practice. The first one, find the next 3 terms in each of the following. For example, here, part A, 1, 3, 5, 7. This is in fact the sequence of odd numbers. Or we can also add 2 to get the next term. So you will have to find the next 3 terms for the different parts. Number 2, describe each of the following number sequences and write down the next 2 terms. Look at the first part, 3, 8, 13, 18. So what is happening in this sequence? We are adding 5. So describe each of the following. What you have to do here is just say add 5. You just need to write down add 5. And then you write down the next 2 terms. Now we move on to a new special sequence called arithmetic sequences. What are arithmetic sequences? In any sequence, if the difference between any two consecutive terms is always the same, we then say the sequence is an arithmetic sequence. I repeat, if the difference between any two consecutive terms is always the same, then the sequence is called an arithmetic sequence. Remember, a sequence is, in fact, a list of numbers which obey a certain rule. Let us look at these examples. Part A, 1, 2, 3, 4, dot, dot, dot. So here we need to add 1 to get the next term. Every time I will have to add 1 to get the next term. So the difference between any two consecutive terms will always be 1. Because we have the same difference, we call it an arithmetic sequence. Part B, 2, 5, 8, 11, and so on. So here we are adding 3 to get the next term. The difference between any two consecutive terms will be 3. So we have the same difference, and it is called an arithmetic sequence. Now part C, 19, 13, 7, 1, dot, dot, dot. What is happening in this sequence? We are subtracting 6 to get the next term. I'm subtracting 6 to get the next term. But the difference between any two consecutive terms will always be the same because I'm subtracting 6. So here also we have an example of arithmetic sequence. But the difference here is that we are subtracting instead of adding as in the two previous examples. Now, let us consider the sequence 4, 9, 14, 19, and so on. What can you notice here? We are adding 5 to get the next term. So here the first term is 4, and we add 5 to get the next term. So the first term is 4. Now 4 is also written as 4 plus 5 times 0. Remember, 5 times 0 is 0. The second term is 9, which is written as 4 plus 5, which is also equal to 4 plus 5 times 1. The third term is 14, which is written as 4 plus 10 or 4 plus 5 times 2. The fourth term is 19, which is written as 4 plus 15, which is also equal to 4 plus 5 times 3. Can you observe these numbers and try to understand what is happening here? So you can see that 4 is being repeated everywhere. 5 also. Here we have 0, 1, 2, 3. For the first term, we have 0 here. For the second term, we can see 1. Third term, 2. Fourth term, 3. Have you observed anything from these numbers? Yes, 4 is being repeated, 5 is being repeated, and then we multiply by one number less than the term. For example, for 3, the third term, we multiply by 2. For the fourth term, we multiply by 3. Now, suppose I ask you to find the 10th term. It will be 4 plus 5 times 9. Why 9? Because we take one less than the term. So the 10th term, T10, I'll take one less. It is 9. And the answer will be 4 plus 45, which is 49. Similarly, if I ask you to find an expression for the nth term, it will be 4 plus 5 times n minus 1. Simplifying, I will get 4 plus 5n minus 5, which is equal to 5n minus 1. So an expression for the nth term will be 5n minus 1. Let us check. Suppose I want to find T10 using this expression. So T10 meaning n equal to 10. It will be 5 times 10, 50, minus 1, which is 49. And we had obtained 49 earlier. Now we move on to this example. Consider the sequence 7, 17, 27, 37. So here I need to find the 9th term, the 120th term, the nth term, and also to find which term is 3107. So you can see here that the first term is 7 and we are adding 10 to get the next term. So the difference here is plus 10 and the first term is 7. So the 9th term will be, we always keep the first term here, plus the difference times 1 less than the term. So the 9th term, I have 8 here. So it will be 7 plus 10 times 8, which gives me 87. Part B, I need to find the 120th term. So it will be 7 plus 10 times 119, and simplifying, I get 1197. Part C, I need to find an expression for the nth term. So it will be 7 plus 10 into n minus 1, and simplifying, I get 10n minus 3. You can check if this expression is correct or not. So suppose I want to find the 4th term. It will be 10 times 4, 40, minus 3, which is 37. And here the 4th term was indeed 37. Now, I was also supposed to find which term is equal to 3107. So what I do, I equate this expression to 3107 because this is the general expression for the nth term. Solving this equation now, I will get 10n equal to 3110 and n will be 311. So 3107 is in fact the 311th term. So now you have a few questions to practice based on the arithmetic sequences. They are questions similar to what we have seen in the examples. We now move on to geometric sequences. Consider the following sequences. What do you observe in these sequences? 1, 4, 16, 64. We are multiplying by 4 to get the next term. Or we can also say 4 divided by 1 is 4. 16 divided by 4 is 4. 64 divided by 16 is 4. So the ratio is same for any pair of consecutive terms. Part B, 10, 20, 40, 80. What is happening here? We are multiplying by 2 to get the next term. Or if I consider 20 divided by 10, I get 2. 40 divided by 20, I get 2. 80 divided by 40, I get 2. Again, any pair of consecutive terms will give the same ratio. The third part, we can either say that we need to divide by 3 to get the next term, or we can also say that we need to multiply by 1/3 to get the next term. So here we have 81 over 243, which is 1/3. 27 over 81, which is 1/3. 9 over 27, which is again equal to 1/3. So any pair of consecutive terms gives the same ratio. When this is the case, we call these geometric sequences. Consider the sequence 4, 20, 100, 500, and so on. Here the first term is 4, and we multiply by 5 to get the next term. So the first term is 4, which can also be written as 4 times 1, or 4 times 5 to the power of 0. The second term is 20, which is 4 times 5, or 4 times 5 to the power of 1. The third term is 100, which is 4 times 5 to the power of 2. The fourth term is 500, which is also written as 4 times 5 to the power of 3. So what can you observe here? The first term is 4, and we can see 4 appearing here. The ratio is 5, because we need to multiply by 5 to get the next term. So you can see here that we have 5. And we have 0, 1, 2, 3. Again, first term, power 0. Second term, power is 1. Third term, power is 2. Fourth term, power is 3. So can you see the pattern here? If I need to find the 10th term, it will be 4 times 5 to the power of 9. Similarly, if you need to find an expression for the nth term, it will be 4 times 5 to the power of n minus 1. 4 is in fact the first term, and 5 is the ratio, or we call it the common ratio. So the expression will be 4 times 5 to the power of n minus 1. Now consider this example. 1, 6, 36, 216. So you need to find the first term, the common ratio, the 10th term, the nth term, and finally, the term which is equal to 46,656. So here the first term is 1. The common ratio is either 6 over 1, which is 6, or you can also say 36 over 6, which is 6, or even 216 over 36, which is 6. So the common ratio is 6. Now to find the 10th term. It's going to be the first term times the ratio to the power of 9, 1 less than the 10th term. You can leave it as it is, which is also equal to 6 to the power of 9, or you can also evaluate your answer. But so an expression for the nth term, it will be 1 times 6 to the power of n minus 1, which is equal to 6 to the power of n minus 1. Now I need to find which term corresponds to 46,656. So I equate the expression of the nth term to 46,656. And I need to solve this equation, what we call exponential equations. So here I divide by 6 until I get 1. So I have 1, 2, 3, 4, 5, 6. I need to divide by 6 times to get 1. So 6 to the power of n minus 1 is equal to 6 to the power of 6. So equating the powers, we get n minus 1 equal to 6 and n equal to 7. So the 7th term will be equal to 46,656. So you have a few questions to practice on geometric sequences. They are similar to the examples. You also have some links where you can get additional practice on what you have just learned. So students, let us see what we have learned in today's session. The first thing which we have learned is repeating patterns, where some numbers will repeat themselves in a regular way. For example, here 0, 1, 2, 0, 1, 2 are being repeated. Then we have also learned about growing patterns, where we need to add a given number to obtain the next term. We have also learned about shrinking patterns, where we need to subtract a given number to get the next term. We have also learned about the special sequences, namely sequence of square numbers, sequence of cube numbers, sequence of prime numbers, sequence of triangular numbers, and we have also learned about two new sequences, namely arithmetic and geometric sequences. So in any sequence, if the difference between any two consecutive terms is always the same, we say that this sequence is an arithmetic sequence. And if the ratio in any sequence between any two consecutive terms is always the same, we say that it is a geometric sequence. For example, here we are multiplying by 4. to get the next term. So the ratio is 4. And we have the same ratio throughout, so it is called a geometric sequence. We have also learned how to find an expression for the nth term for these two types of sequences, arithmetic and geometric sequences. So students, we have reached the end of the first part on sequences. Until we meet again in the next video, it's goodbye from me. Thank you for your attention.